In this lesson, what we are going to do is extend the idea of electron configuration and orbital diagrams and the formation of ions, all three of those things. So electron configuration, orbital diagrams, and the formation of ions to period 4. All right, and we're utilizing the standard configuration that I have written at the top of the board. We're going to emphasize the first 4 periods of the periodic table and realize that if you're going to go beyond that, that you can open up a textbook to find or to at least look at how the electron configuration extends for the larger elements, because as you can see here, when you look at the electron configuration, energy level 3 and energy level 4 overlap, and you see more of this similarity as you move down through the periodic table. For our purposes, we're going to stick to the first 4 periods. So this electron configuration takes care of everything from hydrogen through krypton. So to warm up, let's first look at potassium. All right, it has 19 electrons. So the electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6. This puts us at 18, so we're going to need one more electron, and so we're going to have one electron in the 4s shell for 4s1. If we were to look at the orbital diagram for this, we would write the following platforms. All right, so this is going to be the 1s, this is going to be the 2s, this is going to be, these 3 platforms are the 2p. We make sure to have the labels for everything. And this is going to be the 3p, and then we've got our 4s. All right, and then when we put the electrons in, use some kind of arrow, either a half arrow or a straight-on arrow. But remember that due to the Pauli exclusion principle, which says no 2 electrons can have the same 4 quantum numbers, that the arrows where the electrons are paired up have to be pointed in the opposite direction. This acknowledges the fact that the electrons are operating as magnets. The magnetic force of attraction is offsetting the need for the 2 electrons that are in the suborbitals to repulse one another. So this is the electron configuration in the orbital diagram for potassium, and you can see that the 4s electron is by itself in a subshell. Remember that the orbital diagram allows us to basically identify all 4 quantum numbers for any particular electron. So we're talking about the energy level. Oh shoot, let me fix that. And I'm just going to abbreviate these. If you need to, you can go to the past lessons to sort this out. So this would be energy level. Then we're going to have the shape. Then we're going to have orientation. And then we're going to have the spin number. I'll just put it in there like that, spin number. And I don't know why my equal signs are looking so badly here. Just abbreviate this again. So we have the ML, which is orientation, and we have the MS, which is the spin number. This is the acknowledgement of the magnetic field of the electron. The MS number is the acknowledgement of the magnetic field of the electrons, acknowledging the fact that they cannot be in a suborbital paired up unless they're in a situation where the magnetic fields of the 2 electrons are attracting in order to offset the need for the 2 electrons to repulse one another because they have the same charge. All right, now with the warm-up, I'm going to go ahead and move to scandium, which is shown here, where I captured part of the periodic table. And SC, I'm going to make a little more room here, has 21 electrons. So let's go ahead and look at its electron configuration. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6. We're at 18 electrons at this point, and then we're going to have 4s2 and 3d1. All right, so if we look at the orbital diagram, let's see if we can fit it in here. I'll do this a little smaller. So all right, so let's see, I'm going to change colors. Whoops, yeah, that'll work. All right, so we're going to have the 1s. Whoops. We're going to have the 2s. And then the 3 platforms for the 2p, I make sure to have my label. This is going to be the 3s. Too bad if your hands hurt. Yes, you have to label the platforms so that it's absolutely clear. This is going to be 4s, and then we have 5 possibilities for the 3d. There, everybody's labeled. All right, and then I can go ahead and put in my electrons. Again, the pairs are done in a way to show that the magnetic field is offsetting the repulsive forces here. So we have an arrow pointed up and an arrow pointed down. We just go through and fill the platforms using common sense. The off-bow principle says that we're filling from the lowest energy level towards the highest energy level. Hund's rule tells us that we're going to leave electrons unpaired until we have to pair them. We have a single electron out here in the 3D shell. I'll change the color so that we emphasize that. It's convention, and what I mean by convention is this is an agreement between chemists that we fill these platforms going left to right. So this single electron, which is shown here, could be in any of the 5 options or 5 orientations available in the 3D shell. All right, but by convention, which means agreement, I am putting it in the leftmost platform because by agreement or convention, we're filling left to right. All right, now, and here is a crucial aspect of this. I think what I'm going to do is write it down here next to this arrow so within the periodic table so we can practice this a little bit more. And what is the convention I'm talking about? Well, it's actually not a convention. So what we need to do now that we've got scandium, both its configuration and its orbital diagram, is talk about how it ionizes. So the period 4 elements have multiple oxidation states, meaning that they form many different types of ions. This is different for groups like 1A and 2A, and because remember, when we talk about period 4 here, the period 4 transition metals, right? So we're talking about everybody between scandium and zinc, right, on the other end. So these particular metals, they will ionize to form cations, but they have multiple oxidation states, which means they form, each and every one of them can form more than one type of cation or more than one type of positively charged ion. This is in contrast to 1A and 2A, which form fixed ions, right? 1A forms the +1 cations, and group 2A forms the +2 cations. No such correlation in period 4. These particular elements from scandium through and including zinc form multiple cations. With few exceptions, the zinc only forms zinc +2. So let's talk about how these period 4 elements ionize. This is going to be super, super important because I'm now going to explain a rule to you which you must follow. So I will write it here. So when period 4 elements, period 4 metals, let's do it that way, ionize they preferentially lose electrons from the 4s subshell before losing electrons from the 3D. This is a rule. You must know it. You must, let's just get it out of the way. For a lot of you, you're just going to have to memorize it. It's a rule. You have to know it, and you're going to have to be able to use it. So, let's go ahead and do an example now. So, let's find the electron configuration and orbital diagram for SC plus 1. So I've already completed the orbital diagram for you, and you can see that the electron configuration, and you can see that the electron configuration, if we just look at the valence, right, and the valence for period 4 is going to be the 4s and the 3d. So let me box that in right now. So this is the valence for scandium, right? So period 4 valence, P4 valence, I'm going to write that down here too. This is equal to the 4s and the 3d. Very, very important to know. All right, so SC plus 1, it has lost 1 electron. Where did the electron come from? It came out of the 4s shell. So the electron configuration of the ion is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d1. All right, if we were to look at the electron configuration for SC plus 2, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, and then it will be 3d1. Because period 4 elements, the metals, preferentially lose electrons from the 4s shell before the 3d. All right, now I'm going to go ahead and underline the valences here. So for the SC plus 1, here's my valence. All right, and for SC plus 2, here's the valence. You must know how to write electron configurations for the ionized or the ionized versions of period 4 transition elements. So if I was to do the orbital diagram, I think I can squeeze it in here. I'm going to do it for SC plus 1 as the example. So I'm going to put it right here. So let me rewrite this, SC plus 1. All right, so we're going to have, let me get my platforms. I think I have enough. Let's just check this out quickly. So this is my 1s, 2s, 2p, making sure to get all the labels correct. And then the 5 platforms for the 3D. So again, most of this, it fills easily. Just run these babies out. And then in the 4s, I'm going to change my color to be abundantly clear. We're going to have one electron here, and we're going to have one electron here. This would be SC plus 1. We preferentially took the electron from the 4s shell. With that, I'm going to have a drink of coffee. Okay, so let's look at, we have two exceptions we really should look at here. Let's go ahead and do iron as another example. So let's see, I can fit this in over here. So Fe 26, I'll do the two exceptions on a fresh page, but I'm going to do iron here. So the electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. All right, so let's just gather ourselves, because I know some of you are going to be rapidly counting right now. We're out to 18 here. That means we're at 20 here. So in the 3D, we're going to have 6 electrons. That's how you do this efficiently, by the way. All right, and if we look at a classic ion of iron, right, like in hemoglobin, it fluctuates between iron 2 and iron 3. So let's do the structure for iron 3 plus 3. All right, and we'll change colors here. So we're going to lose 2 electrons out of the 4s and 1 electron out of the 3D. So, and I'm just going to do the electron configuration for this before moving on. So the new configuration, wait, let me be really clear about this. For the Fe plus 3 is going to be 1s2, 2s2, 2p6, that's 10 electrons, 3s2, 3p6, 18, and then the 4s is gone because we preferentially ionize out of the 4s before the 3D. These 2 electrons are hasta la vista. We need to take one more electron out of the 3D, so this is going to be our final configuration is going to be 3D5 for the ion, and I'm going to underline the new valence. All right, now let's look at another shell or new page, and I want to do the 2 exceptions to the rules. So the first one is chromium. It has 24 electrons, and for the 2 exceptions, which are chromium and copper, put only 1 electron and just make sure that I make that clear. 1 electron in the 4s. All right, so the configuration here is going to be 1s2, 2s2, 2p6, we're at 10, 3s2, 3p6, we're at 18, and then we're going to have 4s1, 19, and then we're going to have 3d5. And that should give us 24 electrons. So we had 18 here, 19, 20, 21, 22, 23, 24. Did I say 25? I meant 24 electrons. It has 24 total electrons. I don't remember what I said. It's too early in the morning. All right, and next will be copper for 29 electrons. So its outer valence is going to be, or excuse me, its electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, we're at 18. All right, and again, it's going to be 4s1, and then we're going to have 3d10. All right, which gives us a total of 29. All right, and I want to underline the valences and remind you the valence includes both the 4s and the 3d. So in finishing, what you need to remember about period 4, I would summarize as two things. First, understand that the valence includes the 4s and the 3d. So let's summarize that here. The valence for P4 equals the 4s and the 3d together. This is because the 4s and the 3d shells in period 4 are really close in energy. When I say period 4, I am specifically at this point talking about the metals. So we're talking about not tin, sorry. We're talking about scandium through zinc. Scandium through zinc. Through and including zinc. That's what I'm talking about. And the 4s shell is very close in energy to the 3d shell. So this is the valence. All right, and then the second thing is that for the P4, and again, I'm talking about the same thing here, the metals, Sc through and including zinc, they ionize 4s electrons before the 3d electrons. This is important. And then lastly, make sure that you know how to write the EC and OD for P4, including ions. And really, you need to be able to do this for any element, starting with hydrogen through krypton. Period, period, period. All right, so with that, I'm going to go ahead and conclude the lesson.